Hello, welcome to the video. In this lesson, we're looking at section 3.4, where we're going to look at proofs with perpendicular lines. So, first thing we're going to do is one, we're going to, it says we're going to look at some different relationships to perpendicular lines. We're actually also going to look at how to construct a perpendicular line. And then we're going to look at theorems that are going to help us prove certain lines are in fact perpendicular. Okay, so before we get started with any of these, anytime we're dealing with perpendicular lines, we're looking at the intersection of two lines and they intersect at a 90-degree angle. So first thing that we're going to look at is how to construct a perpendicular line. So here you're going to need a compass and a straight edge in order to do this. So the first thing you're going to do, it says draw line segment AB. So if I go down here and I take my straight edge, and so here is my line segment AB. So I can even label that A, B. Okay. Next, what we're going to do is we are going to construct a perpendicular line CD. So in order to construct this perpendicular line, you are going to need a compass. So get out my compass here, and this is kind of how you're able to construct this. What you're going to do is you are going to put the sharp end of the compass on one of the endpoints. Then what you're going to do is you are going to choose a distance that appears to be larger than halfway of the line segment AB, all right? So it could change for anybody and how you determine um, it's more than halfway. So from here, what you're going to do is you're going to kind of strike a mark on one side of the line segment AB, and then you're going to strike a mark on the other side of line segment AB. Now, without moving the position from the distance from your your pencil to the sharp end of the uh, compass, then what you're going to do is you're going to put that sharp end and place it at point B. Then what you're going to do is you're going to make another arcs on both the left and right hand sides of line segment AB. And what it should do is you should get an intersection like you do on the right, and then move it over to the left, strike a mark, and you should get another intersection on the left hand side. Then what you're going to do is you are going to intersect, make it, take your straight edge and draw a line that goes through the intersections of those strike marks. With that construction, I can tell you now, so let's if I call this C and I call this D, I can say that line segment AB is now perpendicular to line segment CD because of the construction that we made with our compass and straight edge. The next thing they want us to look at is they want us to find the distance from point A, which is right here, um, to line BD. So BD is this line right here. All right, so it's that line right there. Now, when it comes to finding the distance between either a point in a line or two parallel lines, the distance must be perpendicular to the point and that respected line. All right, or if it was two lines, it's going to be the distance between those two lines, and they must be perpendicular to each other. Yes, I agree that this distance A to B is a value, and this distance from A to D is also a value, but they're going to be different. What we need to find is the shortest distance between this point and this line, and it just so happens to be right here, and it actually goes through the line segment AC in this particular instance. So we need to find the distance of line segment AC to find the distance from point A to line BD. We must use the distance formula since we're using coordinates, and if you recall, it's going to be the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. All right, so what I'm going to do is I'm going to call A my x1, y1, and I'm going to call C my x2, y2. So substitute in those values, I get the square root of, and it's going to be 1 minus a negative 3 quantity squared plus negative 1 minus 3 quantity squared. So this is just me substituting those respected x1, y1, um, x2, y2. Here is plus plus, 1 plus 3 is 4. 4 squared is 16, so I have 16 over here plus negative 1 minus 3 is negative 4. Negative 4 squared is also 16. So I got 16 plus 16, which gets me 32. So I got the square root of 32. Now, the square root of 32 is not a perfect square number, so we're going to get an approximation. So the approximate distance from point A to BD is about 5.66 units. Here on this page, we have a few theorems that we're going to use to help us prove some lines that are perpendicular. The first one here is a linear pair theorem. Basically, the conditional statement through the diagram says that if angle 1 is congruent to angle 2, then we can say that G is perpendicular to H. If we have uh, a transversal like we have here, if we say that if line H is parallel to line K and um, line J is perpendicular to line H, then we can make the conclusion that line J is perpendicular to line K. And then the final theorem is the lines perpendicular to a transversal. Basically, it states that if um, line M is perpendicular to line P and line N is also perpendicular to line P, then we can say that line M and line N are parallel. So with that, what we are going to do, it says use the diagram to prove the perpendicular transversals theorem. So if we look at, they want us to prove the perpendicular transversals theorem. So if you look here in the conditional statement, it has um, two givens for a hypothesis. So it's like H is parallel to K and J is perpendicular to H. So if we look at the diagram here, we do in fact have two givens in this diagram. So if we write out our proof, I got my statements and I have my reason. So the first one is I can say that H is parallel to K, and I can also say that J is perpendicular to H. So that is our given. All right, so to look at this the conclusion. They want us to prove that J is perpendicular to K. So same thing here. They want us to prove that J is perpendicular to K. All right. So using what we have here, we're going to attempt to prove that. So right off the bat, using some of the things that they show us, I see that we do have that right angle, and it's in regards to angle 2. So since we have that right angle, I can then say that the measurement of that angle 2 is going to be equal to 90 degrees. The reason for that is the definition of perpendicular lines. All right, definition of perpendicular lines means they intersect at 90 degrees. Next, I'm going to use some of our rules or some of our theorems about angle relationships. And with respect to angle 2, I'm going to use angle 6 to help us out. So angle 2 and angle 6 are both, in fact, corresponding angles. And since H and K are perpendicular, I can say that angle 2 is going to be congruent to angle 6 because of the corresponding angles. Next, because those angles are congruent, I can say that their measurements are congruent. And that is simply the definition of congruent angles. And the fifth step to help us out is, well, since 2 is 90 and 2 is also the same as 6, I can now say that the measurement of angle 6 is also going to be equal to 90 degrees because of the transitive property. And now that I have, and I realize now that 6 is 90 degrees, I can say that it's a right angle. So now I can finally say that J is now perpendicular to K because of the definition of perpendicular lines. Because since we just realized that angle 6 is 90, I can now say that those two are in fact perpendicular. If you look at this example here, what it says is they wanted you to prove the perpendicular transversals theorem using um, alternating exterior angles. So what basically you're going to do is it's essentially the same proof. You're still, so if you look at this one here, you still have the same given and you're still wanting to do the same proof. The only difference is they want you to use alternating interior angles. In this case, um, we use corresponding. So no, alternating exterior angles. Sorry. So you're going to use alternating exterior angles. So the only difference would be is this. There'd be a couple differences. First, instead of it being angle 2 is congruent to angle 6, over here it would be angle 2 is congruent to angle 7. And that reason would be alternating exterior angles. Then what you would say, instead of here, you would just put in now the measurement of angle 2 is now going to be equal to the measurement of angle 7, still the definition of congruent angles. And then you would say here that the measurement of angle 7 would equal 90 degrees, because again, we'd still have measurement of angle 2 in two spots equaling two things. So you could say that's still the transitive property. And now, since it's the 90 degrees would be located here, you could still make the conclusion that J is still perpendicular to K because of the definition of perpendicular lines. So it's essentially the same proof. using a different angle relationship to help you solve it. Finally, here it says the photo shows the layout of a neighborhood, and it says determine which lines, if any, must be parallel in the diagram, and you need to explain your reasoning. So, first off, it says we can look at line P and line Q are both perpendicular to line S. If you notice, they both have 90-degree signs that are attached at the intersections of P and S and also Q and S. So by the lines, by the lines perpendicular to the transversals theorem, we can say that P is parallel to Q. All right, so I can say that P is parallel to Q. Also, line S and T are both perpendicular to Q. So if you notice here, because I got the right angle here and I got the right angle here, I notice that those two are both perpendicular. So by the lines perpendicular to a transversal, I can then say that S is parallel to T. So from the diagram, those two pairs of lines, I can prove that those two are parallel. So P is parallel to Q and S is parallel to T through that explanation. And that is how we prove or use proofs with perpendicular lines. Hope this helps. Until next time.